So in this video we will show you a basic code to analyze make a reservoir simulation and impact of steady state flow in reservoir simulation, splitting the fluids between water and gas. We are in a conventional reservoir. The simulation is a forecast depiction of behavior of tight limestone gas reservoir, considering stress-dependent permeability decline and 10% of initial water saturation, and dynamic capture sweep efficiency. So you have the stress-sensitive permeability decay, and over this, the gas balance, the stress-sensitive decay over times, and you have also this permeability degradation. So you have the permeability in times, how it change, prediction of how permeability will change in the next 20 years. So you have the first times of permeability, you have the dynamic capture sweep efficiency curve and the capture system sweep efficiency in this, and you have also the capture efficiencies, the sweeps efficiencies that will change, and you have the maximum efficiencies of with this multi capture system. In the next 5 years you have the maximum system for the efficiencies of this kind of reservoir. You can set different parameters like reservoir area expressed in meters, the net pay thickness expressed in feet. You set the standard, the medium porosity, the initial water saturation, the initial permeability, the fluid pore pressure, and you can make the permeability models, the production and time reservoir, the simulation times, in this case is 30 years, the max theoretical sweep and pathway. You have several of this simulation. You can integrate this simulation with steady flow or unsteady flow. So you have the following: the ConocoPhillips unconventional gas reservoir, you have the asset value value, dynamic permeability and steady state slip efficiencies, and you have also a prevision with the unsteady flow. We consider the unsteady flow simulation. We have the initial evaluation gas in place, the baseline, the effects of apply electrofracturing technique. We can have a stimulation of production, an increasing of 2.5%, increasing of 2.5% of barrels, and increasing of this 1,500% of production in this unconventional oil and gas. The incremental PV, you have the stress-dependent matrix permeability decay over times. In tight limestone reservoir, you sometimes have causing pore volume compactation and microfracture closure for redeposition of some minerals. We applied the model Pedrosa stress sensitivity equation, and the dynamics matrix decay of reservoir pressure. You have the baseline permeability, the electrofracture permeability, how change, this is the changing of permeability after apply electrofracturing. So if you apply the electrofracturing, you have a great increase of permeability around the capture system, so you facilitate the capture, and you don't stress the reservoir with inducting compactation. So you have the reservoir pressure, in this case, the baseline permeability, and like this. You have several of these lines, and conventional gas reservoir in simulation. You have the sweep efficient and a steady flow. Actual capture system was rethinking by the electrofracture thermal stimulation. Traditional hydraulic fracture make 10% of the advantage. In this case you have a great increase. create water-free electrical breakdown channel, eliminating fluid blockage and significantly expanding the volumetric sweep envelope. You have the gas mass balance, conservation of gas in EGP, cumulative produce remaining gas in reservoir. You have the remaining gas reservoir, produce gas and electrofracturing. So you have several effects of this. Finally, you can make as a prevision of capex of the first investment and the investment to apply the electrofracturing. You have a capex growth of $2.8 million using the electrofracturing technique and make much more efficiencies this reservoir. You have also prevent the geomechanical stability and evaluation of some other effects in geomechanical wells stability.